linear regression. So try to recall the basics, try to recall the concepts that we had discussed in the previous session. So if you remember, the regression is a concept that falls under the supervised learning. So you have the various features, various x values, and there is a particular column which is the y value, and this y is expected to be a continuous variable. What do you mean by continuous variable? It can take any value, right? Any real value. There is no restriction saying that it has to be 0 or 1 or 2 or 3 like that, right? If it is a categorical value, like specifically yes or no, 1 or 2, 0 or 1, like that. If it is a restricted categorical value, then this problem, the same problem is going to be a classification problem, like cat or dog, you want to classify, male or female in terms of voice, like that. So just try to recall what is a regression. You are going to make an estimate of a continuous variable. Example, stock market prediction. What is going to happen to this stock tomorrow? What is going to happen? What will be the rainfall in my city tomorrow? Right? You are trying to make a prediction of it. And that value will be a continuous variable. It's not going to be a discrete, or it's not going to be any categorical value. So just remember that is very important to us. Okay, so we just try to recall what is a regression, and we try to give an example of regression. Okay, so with that, we'll start the session. Let's start the requirement of regression. Maybe I'll try to introduce you to a practical scenario, a practical problem, practical business problem. Okay, so most of the problems which we'll be dealing with the business related data set itself. That is because ultimate goal is to go for a data science, which the basis of data science lies under the business analytics itself, right? Recall one of the slides yesterday where most of the things, the big data and the data science, etc., directly originated from the because of the large companies investing a lot on research on their data, and that's how everything evolved, right? So just try to recall that. So because of the same purpose, I'll try to start with an example. Okay, so this will be the problem. At the end of this session, we will write code together to solve this problem itself. Okay, that's why I'm defining the problem initially. That will be the ultimate problem we have to solve together, right? While learning the linear regression, okay, side by side. So the problem that I want to discuss here, let's say we want to solve this particular problem. That is, I want to predict, see the bike sharing count per hour. In 1 hour, how many bikes are required for a sharing purpose in a particular city? Okay, so what is this? Let's talk about the problem first. Let's understand the problem first, because if you remember the basic steps required, right? 6 different steps. The first step says that formulate your problem. Once you know the problem properly, definitely you will be able to do a appropriate analysis of the data. Data analysis comes into picture. Maybe it consists of EDA plus the plotting of various types of parameters, so that you understand what exactly is required, right, from that data, etc. You will come to know about that first. So that is our first requirement. So in order to go to that level, I need to make sure that you understand what is my problem, right? So the problem is that consider our capital city, say New Delhi. So there are many companies which give their bikes for rent. So the concept is like this: several bikes are parked. You can use their app to register, and you can find where is the nearest point that you have their bikes available. Okay, so you can book a bike, you can make a payment. So you go there. Some key will be displayed on your screen. You enter that on the display that is present on the bike. Bike gets unlocked from the dock. You can take it, you can ride as and when you want, and you can find the nearest dropping point so that you can go there and you can drop your drop that particular bike back over there. Right? So this is what is the user's version. User says that, okay, I can find a bike using the app. Just go there, take the bike, do whatever you want, wherever you want to roam within the city, and find the nearest dropping point. You should go and dock the bike back over there, so that this whole the user's view is complete. Okay, so that's what user does. Now that is not our point. I don't want to use bike. Let us say the company is mine, and I want to predict how many number of bikes are required at a particular station, right? At a given time of the day. Okay, so maybe you see the requirement is completely different for different hours of the day. For example, again, this is a fact that other companies' data, if you observe, you will come to know one thing. During the morning hours, right, the bikes are not available at the docking stations near residential area. Okay, consider, anyway, the city has many areas. Some part of the city will be industrial area, some will be business area, economical zone, then some other reason will be residential, purely residential, right, etc. So you can divide your complete city into several regions for sure. So under such scenario, what has been observed is that during the morning hours, in the sense when people start traveling from their houses to the schools, to the colleges, to the institutes, to the work locations, to the offices, etc., you see that no bikes will be available in the residential area, because people find out, okay, I have a bike here, let me take it and let me go, let me reach it as early as possible. So, right, this is the first point. People observe that, right? You can observe this from the data set. Number of the availability, right? If you look at a column, availability, this is what happens. During morning hours, it's this case. Okay. At the same time, during the same time, when no vehicles, no bikes are available near the houses, you can also observe that there is no space available for docking your bike near the office area, industry area, because everybody took the bikes from different regions of the city and they are coming over there and they want to dock the vehicle back to complete the transaction, but it's not happening. So you see, right, now as a businessman, right, I need to provide a good facility to the user so that he can use it again, I can make more money. So the practical problem comes in this place. How do you manage? So if you have a prediction possible from your side, right, during this season, this particular day of the year, if, right, under these conditions, what are the conditions? We'll see that. We'll be discussing that at maybe in the next 5 minutes. So before that, what is my basic problem, right? As a business perspective, as a businessman, I need to develop a model which can predict the number of bikes required for sharing. That's why the title that you see here in the as a problem statement, I have written, I want to predict the bike sharing counts, right? So what is the necessity, right? I want to expand my business. Unless and until I do the expansion, it's not going to, I'll be making the same profit as what I'm doing now. If I want to have a exponential curve, right? So definitely I expect this to happen, right? Also, I want to predict this prediction actually helps me in predicting the behavior of my customer. Okay, and also I can help this in maybe whenever if at all I see that bike sharing count required is less in a particular week or in a particular season, definitely I can offer more discounts, right? So this is the logic, right? Whenever the sales is low, I have to offer discount so that people can think that, okay, this is working for me. This is better than my own vehicle. Using my own vehicle costs me more. So he's giving me for a discount. Why should not I do? Right? So obviously, so discount prices, Again, you can even run something like a membership drive everywhere. That's a common thing, right? So make them member, give some offers, right? Give some incentive so that they feel happy and they keep using your vehicle always. Okay, so this is the overall big picture of what is called as I am trying to predict the count. So one question normally I get from my students whenever I discuss this aspect is that, isn't the bike count mm, a discrete number? Will it be a regression problem? So normally I get that question. So answer is that, assume the count to be a continuous variable. You may get 28.5. So problem wise, you take it as a regression problem. But since, as you told, yes, the number is a discrete number, make it to the next integer. Okay, when the answer comes 28.5, make it 29. Okay, so answer wise, make it discrete, but the problem wise, take it as a regression problem, make that variable, count variable, as a continuous variable. Okay, so that's the solution to the one normal question which I usually get. All right, so how this problem becomes a data science problem, right? I want to predict the count. Count in the sense, how many bikes are required at a given hour of the day in a particular point or in a city, let's say. Okay, so what does that mean? This count, as I just now mentioned, it's a continuous. Okay, make it as a continuous variable. So now, so far as per our understanding, we need a data set for that. Like we have some of the quantities, some of the features, x1, x2, x3, x4. Like we will be having a table. In the table, there will be many features, x1, x2, x3, x4, x5. Many features are there. Depending on those features, I should be able to predict something which is the last column, say y will be the count. So from where do you get that, right? You should have done some observation already because of your business. So again, for our for the class purpose, I have a data set available with me, okay, collected from a city. So that actually has the following features. Okay, so I have to have given I have to have this. Given other features, I should be able be in a position to predict the count of the bikes required for Shent. Okay, I hope the question is very clear, right? So there are many parameters available. There is a data set available. The last column of that is a count variable. We'll assume that it to be a continuous variable and we'll feed it to the machine. Machine has to perform what is called as a linear regression, right? How it performs that, what is the math behind that, is what we are going to look today. So before that, I made clear that this is my problem. This problem is the one which I want to solve by doing the coding. Okay, now let's quickly look at the overall big picture of the data set what we have. All right, so let's say I'll call that that part as the data munging part. So I need to get insights of my data. If the data is not in a proper format, I have to convert it. So these are the various steps. If you have not a numbers, deal with that. If you have unwanted characters, unwanted things in there, missing numbers, missing characters, missing values, deal with that. Okay. Also, you can find out the outliers if you have some outliers in any of the columns, you know how to deal with that. So everything we have done that. Okay. So that whatever we have studied earlier, we are supposed to apply that right now. Okay, so let's see what is the what are the various features available in our data set. I'll try to brief it out quickly so that we understand the data set now, so that we save that time when we actually do the programming part. Okay, so this actually helps us in understanding the problem better, and also this will help us at a later stage during the programming part. So there is one column, the column heading, assume that this is a Panda data frame. So in a Pandas data frame, I know that each column is can be accessed by a particular column name. It's a Each column is a panda series. So there is a column name available, right, to address that whole column. If you want to access the whole column, you can simply use data frame bracket, mention the name over there inside the inverted commas, and you can access that, right? So remember that. So that's what we are trying to, right, to do here. So there are several columns available. So what are the columns available? I'll write the same name that is available in the data set. So the first one is called as the name given over there is DTE day. So what do you mean by it's hourly date? In the sense, 20 say it means 4th September 2022 morning 9 to 10. What happened? That's what is the date, right? So next, the next value could be same 4th September 2022 10 o'clock to 11 o'clock, because everything we are dealing with hourly. So if you observe the question that I have written, I want to predict the hourly number of bikes required, okay, for sharing. So on an hour basis, we are supposed to calculate that. So this is hourly date, hour and which day it is. That's what is written. Then we have another column called season. So there are seasons written in the form of 1, 2, 3, 4. Right? We'll discuss about the data set later. Now, if you see this carefully, 1 will represent a particular season, like say spring. 2 represents a summer. 3 will go for a fall. 4 is the winter. So you see, this is a categorical data. So there are only 4 possibilities: no 3.5, no 2.5, no 1.5, like that. So this is called as a categorical data. Correct?
Sir,
So
what is the first data?
It's hourly date. Okay. Hourly date represents which date, which hour. Okay. On today 10 to 11. Say tomorrow 11 to 12, like that. So hourly date is what. Then, right, you can have what is called as whether it is a holiday or not. So holiday is a column. So you will say yes or no over there. 1 or 0 may be present. Okay. Then you also have, right, something called as yeah, I think we have what is called as a working day. This is the name of the column. Okay. So whether it is a day, working day is something which is neither weekend nor holiday. So yes or no will be there. Okay. 1 or 0. So that kind of representation is what we see there. Then we have a few more columns like
type of bike,
the temp. Okay. Yeah, I'm telling whatever data is available with me. Yes, if you can collect, definitely we can go with the other columns as well. All right. There is something called as a temperature. Okay. Then we have the humidity, right? Because these are the factors affect whether people use bike or not. Because if it is hot, temperature is high, a very humid day, people might not choose to travel by bike, right? Because of that, we have these reasons available. These variables are available as columns. Then you also have the wind speed. Okay. And let me write few more points on the right. Okay. Then there is what is called as, I think, yeah, this is a casual. Okay. Then you have registered, in a sense, casual in the sense, I'm not a member. I can still pay and I can use the bike. So whether you are a casual, how many casual users are using, how many registered users are using, that's what is casual and registered. And ultimately you have a variable called the CNT. This is the count. So given these parameters, date, season, holiday or not, working day or not, what's the temperature, what's the humidity, many more columns do exist. I'm not touching everything right now. Just I want to give a big picture, what is there in the data and what we want to do. So given those parameters, date, season, whether it is working day or not, holiday or not, what is the temperature, what is the humidity, what's the wind speed, etc. Given that, you are supposed to predict what is the count. What is the number of bikes required for a given particular scenario? So you see, we have our data set.
sir.
Yeah, please go ahead.
Sir, in the casual and registered, it will also give us the count, right?
Sorry?
In the casual and registered column, it will also give us count, because we can count the number of casual customers and we can also count the number of registered customers.
Coming to that point, okay, please hold on. I'm actually in the next discussion, you will be seeing that I will leave some columns, because whichever columns I don't want, I can leave, right? So I'm coming to that, right? So your point is right, I'll come to that. Okay, so you see, this is the data set that is available, right? So that means normally let me call that the data set is presented in the following format. So x1, first column, whatever is the name, I'll call it as x1. Okay, so maybe it is the date and date. Then I have x2, then I have x3, like that. I have many various parameters. Okay, so say x right, xn, right? So there are, okay, I'll go with the xn, because later on we'll be using n for columns. That becomes easy for you to understand. Okay, so this is xn, n number of features. I call the every data that is available, right? Like, what's the wind speed? Wind speed is a parameter, right? It's a feature. So that is a particular column, right? Like that. So these are the various features available for you. Okay, and at the end I have a y, which is what I want to predict. Correct? So according to this problem, this y is the count. I want to predict the count given that all other set of parameters, right? Right? That's a data set. Now already you remember, data set is something like which contains each and everything, right? Which is observed, right? And you might have to make a little bit of modifications in that, so that you will retain certain things in that, and the program will perform the required what you call guessing of the rule which relates x to y. So this is what we have seen, right? So let me try to write it quickly. I have a table given like this. So in this in the given scenario, you know that I have given some of the x1, x2, x3, etc. Right? Practical data we'll see later. This is just for introduction purpose to understand what we are trying to do here. So this is the column heading, like the name of the series, and the final one is the label. In this case, it is not label; it's a count value which I want to predict. So you see, row wise, I give different right values of each of the parameter. The first observation, right? This is the date. This is the time. Okay, this is the wind speed, this is the temperature, this is the particular. So at that under that 1 hour which I am considering, I could observe all these values for the different values, and I observe that the number of bikes required for the given parameters x1, x2, x3 up to xn is say 500. So the next row says a different scenario, right? Temperature is double, humidity is half, and okay, other parameters. Okay, whatever was given there, you see that completely different. It was not a holiday. Previously it was holiday. Now it is not a holiday, and I can see that it is right. It is not a working day. Something like that. You see, many other parameters will come into picture, and I'll see that the count is completely different. So like that, I will have a lot of observations. Correct? So that observation is what I'm going to call, right? So this is the last number is this is row number 1, row number 2, and I can say the row number m. Okay, this is row number m. M different observations, n such columns, n such features, right? If this is given, I am supposed to predict for any such scenario is given to you, you should be able to predict what is the value of y. So y, as of now, it makes sense that it has to be a whole number or integer, but you will take it as a continuous variable to solve, because machine prefers to solve in that real number way. And anyway, since our requirement is a whole number, convert that into a integer to get an answer that we deserve. All right, so this is what is required. Now my big picture, what I want to solve is I want to solve y is equal to, right? I have to create a function that relates, right? That relates like this. I'll just write h is the function which relates. what you are trying to relate? You are trying to relate x1, x2, x3, x4 up to xn, right? And you will define, right? You will ask the machine to find out a parameter based on which it will identify and it will be able to make a guess. That parameter is what we denote it as a theta. Okay, what is theta? I'm going to come in the next thing, but remember that there is a parameter. That machine has to do a calculation. Something like if you have y equal to mx plus c, m is a slope, that becomes a parameter. Okay, so mx plus c is an intercept, that is also a parameter. Correct? So like that, you have to give some freedom to the machine so that it can make some adjustments, right? In terms of maybe the same thing, like the slope, like the intercept, etc. Something like that. If at all you are asking machine to calculate something like that, you have to give a freedom to that. So that is the parameter is the one which, right, it corresponds to this aspect of the problem. Okay, so that's how we define our problem now. So now I think the problem is very clear, right? So this particular problem, as we understood now, I have to predict a continuous variable. So that falls under what is called as the regression problem, in which right now our aim is to study what is called as a linear regression. All right, so let me simplify the problem for the time being, otherwise mathematics will become too tedious. Let us try to assume that, see, the table says there is a value y, correct? Y can be 500. Now, given the parameter, after the machine learns something, and I give the same parameters x1 to xn, it is expected to generate 500, but there is always a very minute error. So it may say that 499, 495, 505. Okay, absolutely fine. So you see, machine makes a prediction, right? So y, if you remember y is the value that is expected, right? Let me try to make a different notation, y cap, that is a prediction. So machine is going to perform a prediction that, so it depends upon how good is the machine learning. Okay, so y cap is what we are expecting from the machine. We also expect that this y cap is very close to 1. Okay, so that's what is the ultimate goal. Anyway, we'll come to that at a later stage. Now, what is the idea? The idea is that I'll modify my previously written equation, that y cap is equal to, I'll try to write, okay, I'll try to make a modification here. So just look at this part. All right, so I'll try to modify. So see, these x1, x2, x3, x4 up to xn is already known, right? It is known to us. So I don't have to do any calculation over there. So what I am supposed to do here is I have to teach the machine that how the machine can obtain the optimum values of theta. Theta is the parameter which decides the relationship between x1, x2, x3 up to xn to y, correct? So the theta is the parameter the machine should select very properly so that it can relate the x1, x2, x3 up to xn, whatever features it has, to the y. So the standard notation, even if you refer the textbooks or any internet material, they will say that this is h theta. H theta of, because theta is the parameter which you are estimating for the given x1, x2, x3, up to xn, right, with the theta. So that's the notation. So I'll make the same notation here, h theta of. Now I'll assume that I don't have many columns with me. I just have, say, 2 columns. What are the 2 columns? Let's write x1 comma x2. Only 2 parameters. Okay. And my intention is to teach the machine how to select the optimum parameters theta so that I can make a prediction y cap. Okay. So actual data set has many columns, but right now, for the simplicity of understanding what happens on the background, how the mathematics works, for this, I am taking only 2 parameters. I hope this is fine for you. Okay. So since our problem is called as a linear regression, what we are supposed to do here, our intention is pretty simple. We have to fit a straight line. So what do you mean by the straight line? That should look like this. Y cap is equal to, see, x1 is your value. So if you go for a simple scenario, that if this is my straight line, I say y is equal to y versus x. So this is equal to y equal to mx plus c. Okay, if this is what we are calculating, y equal to mx plus c, what is your input? Input is x. X will be put up over there. M and C are my parameters, so that I can fit a line for y. Y equal to mx plus c. So this is what happens in general. But now you see how many inputs you have. You have inputs x1 and x2. Correct? So theta are the as many number of parameters you want, you can use. So theta is, in the sense, it's not just one parameter. Just understand, theta can be theta 1, theta 2, theta 3, theta 4. As much you require, you can use. But all of them should be optimum, so that I can relate x1 and x2 to the y. Correct? So that's what is the same implication that is happening here. So M and C should be very proper, so that you represent the straight line. If the M and C are different, you may get different points here, right? So that may not be lying on your straight line. Okay, so that's the point. So now let me write it in this way, because linear regression means fitting a straight line. So what are the parameters? I'll call the parameters theta. I denote it by theta, but actually theta will be many numbers. So like this. So you see, this is x1, my first parameter, into theta 1, plus x2, another parameter t2, like m1 x1, m2 x2. If you want m to be present, you are comfortable with the straight line in m1 m2 notation, yes, definitely go with that, right? Write it in that way. Plus the intercept comes into picture, so that is what I am going to call it as a theta naught. x1 theta 1, x2 theta 2, plus theta naught. Now you see that theta, actually whichever I called as a parameter, you can see that there are three, right, values present in it. One is theta 1, one is theta 2, one is theta naught. All together, I'm going to call them as theta. All right. So this is linear, because I can see that it's a straight line. Obviously, everybody can understand that this is the equation of this. Yeah. Sorry. So we know that this is the equation of a straight line. Now, in general, because this equation is not a suggested format for what you call for the mathematics purpose, or for writing the codes for computers. What do you prefer? If you remember, linear algebra is preferred. Everything has to be represented in the form of a matrix. So when you come with the matrix notation, it becomes easy for writing the code. It becomes easy for handling the data by the computers, by the software, and also to provide the answers to us, so that you can visualize something. So for that reason, now I understand that the theta, which was my parameter, that has three different values. One is theta naught, theta 1, and the theta 2. So you see, I converted that into a vector form. That is a matrix form. Okay. So why you need to convert? Because it is preferred to write in that way. Otherwise, I have to enter theta 1, theta 2, theta naught separately. Now, write it in the matrix. It is easier to handle for us, for the computers, for the software, for everyone. So, matrix method is what is preferred. Now, I can say that if I try to convert everything into the matrix format, this is what is preferred. So, I can call the y cap is equal to capital X into capital theta. Right? What is capital X? Capital X is the matrix that contains my various values of x1, x2. x1 and x2 are the columns, right? Temperature and humidity. So I have various values present for them. So that I can give everything, the first two columns, I can make it a matrix and I can put it over there. So what is the size? What is the size of this expected one? So you can see there is a theta naught also coming into picture. So because of which I have to add a column to that. So for example, I can try to write this is x1, this is x2, and I have to write a 1 over, because that is corresponding to this theta naught, right? So theta naught gets multiplied by this. Theta 1 gets multiplied by this, theta 2 gets multiplied by this. So theta 1 into x1, theta 2 into x2, and theta naught into 1 gives you that complete equation like this, right? So maybe the order you might have to change slightly. Theta 1, theta 2 should be exchanged. All right. Anyway, So when you do that, you understand that this is how my capital X should look like. I have to add a column. Though I said that I have only 2 columns, I have to create a third column just to satisfy the condition of matrix multiplication. Okay, so let me write it very clearly for your understanding, so that when you get this material, when you read it, you should be in a position to understand. So I have x1, so these are the first values, then the x1 second value, x2 second value, again 1. So this is x1 third value, x2 third value, 1, and so on. You have to create a matrix here, okay, containing all the data that you have. So what should be the size? There are m rows, and I know that there are n columns. In this case, n equal to 2. When n was 2, I created n plus 1 column, that is 3 columns, because I had to add a 1, 1, 1, 1 over there, right? Now you see, if at all it is generally n column, considering complete data set, you have to have, sorry, my mistake, I wrote m here, this has to be n. So m cross n plus 1 is the size of this matrix. Agree? Okay. Similarly, I have a theta coming into picture. So this will be the various theta values present over there. If you see right now, I just have theta naught, theta 1. Just see, write it in the same way. It is theta 1, theta 2, then theta naught. But in general, this will be, what's the size? It's a n plus 1. So many rows into 1 column. So column is 1. That's obvious. Why it is n plus 1? I have to add something corresponding to 1, right? So there is a 1 added here. So for this one, if you have to multiply by theta naught, so for your n equal to 2, I should add another value to that. So this is n plus 1. Normally you have n equal to 2. 2 plus 1 becomes 3. So you have to enter at least exactly 3 values. Okay, so this is the size required. Now the linear algebra says you have to write it in the appropriate format. So I can write. So this implies the y cap equal to, this is the exact notation, theta 1 times all the x1 values dot dot dot, plus theta 2, my second parameter, times all the x2 values, the second complete column, okay, plus a theta naught. Now you see, this actually is the one which we have written earlier in a different way. So see, theta 1 x1, you have theta 1 x1, theta 2 x2, theta 2 x2, you have theta naught, you have theta naught. So it's actually, I am writing the same thing, but right now the second equation which we have written so far is actually representing the data in the column wise format, because I told that everything comes in the column wise format. The complete column has to be the same data because of this reason. Everything, though I have to decide a parameter theta naught, theta 1, theta 2, etc., I'm multiplying them with a particular column. So you see here, if you relate this to the normal straight line, so this theta 1, theta 2 will indicate the slope in corresponding dimension. And this theta naught actually represents what? That is a bias. It's called as a bias, okay? Or you can, okay, bias, if you are not aware of, bias will come in the neural network. I don't want to use that word right now. Let me use this as an intercept. All right, so that makes more sense, I guess. Okay, so practically later on, we'll see the machine learning terminology. When we go to deep learning, everything changes, okay? But anyway, this is fine. We can stick with the intercept, okay? And these two will be the representation of the slopes. Yes, please go ahead.
Sir, in the last time where y cap equals to theta 1 multiplied by x1 value.
Yeah.
Right. In the multiplication of matrix, we do the row into columns, right? Like every row to the every column.
Okay.
Right. So here we didn't do that.
Where you are saying?
So I'm not getting the last part.
This one? You're talking about this matrix multiplication, I guess?
Yes.
Right.
So from this you get the last equation, right? So I'm not getting that how exactly, because from every column to every row, so theta 1 should be multiplied by x1, x11,
just hold on, I'll answer.
x12.
I understood the question. So you see, you multiply this with this, plus this with this, plus this with this. Correct? Hope you are okay with that.
Yes.
Next step, below that, what you write? You write a single value. Okay, so you can try to write this as, right? So you see, this is actually pretty much basic. That actually stops our flow. You see, right? I will write like something like this: x1 theta 1 plus x2 theta 2 plus 1 times theta 0. Correct? This is my first value. As per your rule, I am multiplying. Next value you write.
Right.
This is x1 second value into theta 1 plus x2 second value theta 2 plus 1 times theta 0. Isn't it? Like that, you have many values coming up. Correct? All the values.
Right.
This is your resultant matrix. Are you okay? So can
Yes.
I write like this? This matrix itself, can I, you see what is common for the first column?
Okay.
Theta 1?
Put the common.
Right?
Right.
So take theta 1 outside from that. So I get this.
Okay.
Right?
I got it now.
So you see here, this is my answer. That's why. Correct? So theta 1 is
Right.
taken out, first column is written. Plus theta 2 taken out, second column written. Theta not, everything is 1, 1, 1. I'm not writing that. Very simple. Okay?
Right.
Hope that is clear. Fine. Now, so our terminology says that the theta 1, theta 2 represents the slopes. This is what I'm supposed to find out. When I say I want machine to perform what is called as a linear regression, I have to, right? I have to ask the machine to find the slopes first and the intercept. This is the fundamental equation which we are intended to do. Okay. Now, how do you say machine starts with some initial value? Maybe you will give a freedom. Choose some random values for theta 1, theta 2, theta 0, and it will start operating on that. Okay, so now let me write the same equations once again so that we get a different picture of the same thing, right? So what I told, I asked the machine to do this. Do me a favor, make an estimation based on a particular column x1, take your own parameters, say theta 1, x2, theta 2 plus theta 0. Correct? This is what I asked the machine to do. So what machine will do, if at all the columns which we have chosen are, say, temperature, the temperature value times theta 1 plus maybe I'll assume it actually has taken the humidity. Okay, the humidity value times its corresponding theta 2 plus theta 0 is what it is going to use to make that estimation y 0. Right? So initially start with the specific value, any random theta 0. It may start with 0.5 as theta 1, minus 0.5 as theta 2, and theta 0 maybe plus 1. So we have, we don't restrict that taking any value over there. Assume that it is random. Fine. Okay. So actually, when the machine learns, we expect the machine to change these values of theta 1, theta 2, theta 0 in such a way that any given value of temperature and humidity should produce the appropriate y cap which is closer to actual answer y. I hope that is clear. All right. Now, so this itself is what? This itself is my count. Let's assume the count variable comes from this. All right. Now, you see, we have a situation here that how do you decide? How do you decide when to stop? How do you decide when to stop? Can anybody answer that question? See, because I have say 1000 rows, m equal to 1000. Now the number of rows equal to 1000. I will give 1000 data, right? I give all the 1000 rows one by one, or many ways are there. We'll come to that at a later stage. I train the machine. I call that as a training. And even after training with 1000, if it is not sufficient, I will go once again. I'll repeat them. Okay. So machine keeps on learning in the sense optimizing this theta 1, theta 2, theta 1. Now I have a question, right? That when do you stop? What is the parameter that you are going to use to say that, okay, now stop learning, because you have learned enough, you stop. What is that parameter that you are going to use? You can create your own parameter, no issues, absolutely fine. This is just an open discussion. Okay, please go ahead.
So I guess when we get the value, closer to the count.
Closer to the
When
count?
we get
Yes.
yes,
Okay.
sir.
Okay.
Or exactly count might not be possible, but the value, if it will be closer to the count, then we can stop the machine to learn.
Okay. Okay. Maybe that answer is the one which close enough. Let's look for other answers. Somebody might give an exact answer. Let's see. Yes, Ruchi, please go ahead.
And sir, when the difference between the actual and the predicted value is as minimum as possible.
As minimum as possible. Yes. Yes. That's good. Next. Anybody? Okay, let's discuss the answers that I obtained. Both are pretty much closer. It says that whenever the predicted value, can I call that as y cap? Okay, that's my predicted value. And let's say the actual value count that is equal to y, right? So somebody said that it has to be close enough. Can I differentiate and try whether that is equal to 0? It's the same thing. Both of you told the same thing, right? So difference between y cap and y equal to 0 means what? They are same. Correct?
Yes.
Y cap equal to y. This is what I want to this. Now you see. Okay, I'll come to another question. With this itself, I have another very interesting question coming up. Let me call this as an error. Okay, let's say that there is an error term. Error is equal to y cap minus y. I will just stick to this. I will not write the other part. So for every data point I feed as input to the machine, which is learning. For every y it actually predicts a y cap, I will take a difference. Let's say this is the error. Now you are saying that if the error becomes equal to close to 0, because obviously it may not be equal. If at all it's close enough, you will say that you stop learning. Correct? So you have to stop this. Now, again, individually, it may not be appropriate to stop the learning instantaneously because I have say 1000 rows. I start giving the different values one by one. The first row, second row, third row, fifth row, one by one. Let's say I'm giving. Okay, the learning is not complete. Somewhere in the middle, one of the value for one of the row, y cap minus y become equal to 0. Will you stop? Will you stop learning is my first question. Yes or no?
Yes.
You will stop?
Yes.
Oh, no,
because we get the value.
The complete data set is not at all. That's my first point. Because machine has not faced each and every aspect of the parameters. Okay? So everything is not over. Just maybe I had 1000 various rows, out of which just 500th row itself, it became only one. That value it becomes 0. Okay, will you stop? Was my question. So somebody said yes. What the other answer we may get?
No, sir.
No. Devendra says no. Why not?
Because we have to go end.
Every type of data machine should learn first, right? Machine should face that first, then only you can come to an answer. So yes, so that's a correct answer. Okay, we cannot stop there because we have not made the machine to see each and every type of feature. Correct. So one of them becoming 0 is just something like it's by chance. That's all. Okay. For everything, if it becomes 0, yes, you can see. Correct. So how do you make sure that for everything it is 0, you will take the sum? Because y minus y, y cap minus y, if it is 0 for every value, your sum is also 0, right? For the whole table, isn't it? Correct? Am I making the point clear? Let me write that so that when you refer to this, it should be clear to you. So what I mean here, let me say that I have the temperature value here, let's say that is x1. I have the humidity value here, let me call that as x2. There is a y value given here, there is a prediction y cap that is happening. So I start with x1, not x1, sorry, I cannot write x1, x2 here, my mistake. It's a row numbers. Okay, so first row is the first data, second row, third row, like that. I give all the m rows. Okay, so this is row number 1, row number 2, row number 3, all of them, right? So maybe you can add another column just for representation of the error. All right. Now, so the point is this. Let me make a table clearly. So this is the temperature data, this is the humidity data, this is the actual count which we have observed, and this y cap is the predicted value. Now the question is that when do you stop? So earlier situation was somewhere in the middle third term, the y and y cap becoming equal. So I asked whether you stop. So the right answer we obtained was no, you cannot stop because many things else it to come. So you have. Now how do you make sure that all the values are equal? How do you make sure that every value in this column y and y cap are equal? How do you make sure that? Right?
By taking the sum.
Taking the sum of the error, right? So calculate error, add another column, right? Let's say that is y minus y cap. That's my next value. If all the values are 0 or close to 0, your sum should be equal to 0. Right? Is it valid point? Okay. So let us say I'm calculating y minus y cap, right? For everything, every input, I'm calculating y minus y cap. That's my error term. I have a complete new column which says that is the error, right? I'll take a sum, and if it becomes equal to 0, I am asking another question now. Can I stop? So far, I told yes, we can stop. I'm repeating the question. Can I stop? Is there any problem with this? Please think and answer. Slightly tricky question.
Sir, could you repeat question again?
Yeah, my question is that, so I'm actually creating a error column over here. The last column which you see, okay, I'll slightly move further to the right so that everything comes into this. So I added a new column, right? So this is the error term, right? So far our discussion said that if y and y cap are equal, correct? Y and y cap are equal, error becomes equal to 0. If you get a single term 0 in the whole table, that is not the end of training, correct? Yes. Now what is the solution? We are thinking that, okay, let all the columns, right, all the error values in that particular column become equal to 0 so that we can stop. So that is what is our idea, and that is right. I am not raising any question with that. I am asking, I'm raising a question with respect to my method. My method says that if I add the last column and if I get a result equal to 0, can I stop? Is my question.
No, sir.
Okay, so we have one answer from Devendra saying no. Can you justify that? Can you try to elaborate? Why?
Because, sir, very difficult to find out end point. Because
not an end point. For example, let's assume that our intention is clear, right? I am calculating error for each of the training. If every value in the last column is 0, my logic says that if I take a sum also should be equal to 0 so that I can stop. This is my point. Okay. So assume that all the values in the last column are 0, 0, 0, 0, everything 0. When you take a sum, what happens? It should be 0. It should be 0 means what? All values are 0 is what I think. So I ask the question whether it is correct. Whether I can stop if I get 0 is my question. You said no, and I expect you to justify why it is wrong. Why the adding all the terms and becoming equal to 0 says that you cannot stop. What could be the possible reason is what I am asking.
okay,
It is like we are adding the data, right? We are not looking into individual observation. So there would be huge outliers also into that observation, which could be nullified due to different reasons, right?
Yes. We are close to the answer. That's what was expected. Yes, please go ahead. Somebody else was also trying to answer. Anybody else?
If we get sum is equal to 0 for the error, it doesn't mean that for each entry we get 0.
Yes.
It may be -1, it may be +1, and
Right.
sometimes or like that.
Correct. So that is a problem. So both of you have given the similar answer in your own words. Let me say that this is not 0, this is +100. there is somewhere else I have minus 100. You see, all of them are not 0, but taking a sum will give you 0. So my intuition was wrong. I just thought that, okay, if all are 0, I take a sum is also 0. But this is the other possibility. So I have another problem to think, okay, the method you calculate error is not correct. Am I right? So whatever term I'm using as error, that is not correct. Isn't it? All right. So what is the solution? So how can you define, how can you change your definition of error? Initially, I told that I am going to consider the y cap minus y. All right. I cannot call this as error anymore. It's not a valid thing. Right? So one solution comes. People will say that take absolute y cap minus y. Make a magnitude of it. Okay. Even if it is negative, convert into positive, because I don't have to do anything whether it is negative or positive. I need a magnitude justifying that, yes, there is error, right? So this is what is called as magnitude error. Okay, it's MAE. All right, that's a one thing, right? Absolute error. Okay, and also there is another one. If you might have seen this as well. It's a squared error. This is y cap minus y squared. Magnitude of the squared error. This is absolute error. AE stands for magnitude of the absolute error. You take a magnitude. And the second one is a squared error, right? Both are going to work pretty much fine, right? Both are going to be, right, converting your negative answer into the positive answer. Okay, so normally it's not that you have to stick to only squares. You can go to the power 4, power 6, power 8, power 10, anything will work. Okay, so but we don't want complications, right? I see the squaring is easier compared to taking a 4th power, 8th power, 12th power, and so on, right? So other than any odd power, you can keep anything as your standard error. Okay, so that's another thing. We'll discuss about the errors in a different concept, but right now you understand that this is what we need. So we will define, right, MAE or MSE as the error. I hope that is clear, right, for the time being, right? So we define our the error function, or so there is another term here, right? The technical term used in the field of machine learning is a loss function. In the sense, if there is more loss, right, you need to do more training. Why it is called as loss? Because you are losing your computational power. In the sense, you need to do more and more training. More and more training needs more and more power in terms of the electricity, more and more time of your computer processor, right? Also your time. You have to wait. Doing nothing, you simply have to sit and wait until the training goes on. So that's why this is what is called as a loss function. More loss indicates more training is necessary. If the loss function is less, indicating that, okay, right, so you can, right, and normally we define a threshold in terms of the loss. If the loss is lesser than this, you can accept the result what we obtain. Okay, so that's what is the significance of what is called as a loss function. Now I'll come back to my problem. What was the problem? So the fundamental idea was that I have to select the theta values in such a way that the theta values are to be optimized, such a way that my y and y cap come as much closer as possible. So can I try to write like this? That is, so the loss function for a given theta, because right now I have a theta value, that theta value generated a y cap. So that y cap minus y whole square, which is my loss function of a given theta, either it is more or it is less. So can I write this loss function? Loss function is normally denoted by L. That's why I'm writing a L here. So the loss function of the given theta is actually denoted by the y cap minus y the whole square. Let's stick to this one because this is the very standard one. Why I'm using y minus y whole square as the standard function, I'm going to justify that in a while. Okay, so just hold on. Now, what is y cap? In the matrix notation, if you remember, that is x theta, just the previous page, x theta minus y the whole square. This is what is my loss function for a given theta. Now, what is my goal here? My goal here is to teach the machine. What do you mean by teaching the machine? Machine has to identify the theta values. What are the theta values? Theta 1, theta 2, theta naught, etc. Now those theta 1, theta naught, theta 2 have to be selected out of all the possible infinite values. It can be minus infinity to plus infinity, each one. Theta 1, theta 2, theta naught can be anything out of it. But the machine has to select them in such a way that, now you see, this is the optimization. This is the optimization problem. Okay, the optimization has to happen in such a way that, right, the L loss corresponding to the theta should be minimum. Correct? This has to be minimum, right? Because I cannot say make it 0, because already we know that both the columns cannot be equal to 0, right? But for various theta 1, theta 2, theta naught, it can actually try to make an estimate of y cap, so that we calculate y cap minus yb whole square, take a sum. For the complete set of theta 1, theta 2, theta naught, I'll make a calculation. I get a loss for that particular theta. I'll modify, I'll go back, I'll check it once again, right? With the different value of theta naught, that may reduce. So I have some idea that which direction I should go. What should be the values of theta 1, whether it is to decrease, whether I should increase, something like that. I'll come to that part, whether to increase, decrease, how do you decide, etc. Will be coming to that. Now the goal of this problem now becomes minimization. Minimum, find out the values of theta such a way that this L of theta becomes minimum. Correct? So now you see another point comes into picture. This is what I am taking from the calculus, right? L of theta, loss corresponding to theta. Theta is a parameter, loss of theta is a function of theta, L of theta. So how do you minimize that? That means I have to perform dou L by dou theta and equate it to 0. This is finding minima point. Are you okay with that? I think you should be able to recall some basics from linear, this is coming from the calculus, differentiation, applications of differentiation. So this is what we are ultimately trying to do. Okay, so this term is what is called as a gradient, rate of change, basically. Right? When theta slightly changes, what happens to L, right? We'll be using this at a later stage, but I'm trying to define the various terms required. All right. Now we are using a very standard theorem. Okay. So this theorem is the result of the whole analysis of the linear regression. Okay. So now we deviate. Now we make sure that we go in two different paths. The path number 1 is what I'm going to discuss now. This is for those who don't want any mathematics. You say that, no sir, you just tell me what is the final equation. I don't want to know how you get that. So I just want to know that this is the equation I should remember, so that I can apply the linear regression to any problem. If, right, few of you belong to that category, then look at what I'm going to write. Okay, so this is applicable for those who don't want mathematics. I say that no, I don't want to go into the mathematics at all. Right? Just tell me the equation which is as a result of some derivation, you come to this equation. But this equation is important to apply the linear regression. If you are of that category, right, observe something that's going to happen next. So this is what is the result. I'm directly coming to the result. So that is, so if, let us say, if you use linear regression and you use the MSE, mean of the squared error, right? So that square term, that's why I told I'm going for a square, not the absolute, ME. If linear regression is what you want to perform and the error you want to use is mean squared error, then the theta, optimum value of the theta, you see, directly I'll come to the optimum answer. Right? What are the various optimum values of the theta you want? That is theta star. It's a star in the sense it's an important. Okay, not a general theta, not any arbitrary value of theta. It's the ultimate answer, final answer, directly one step answer. So that is, take your x, it's a transpose into x transpose, multiply that with x, take its inverse. Okay, multiply that with x transpose, into y. Very simple. You see why we mentioned that we need linear algebra, why we need matrices, etc. So many things we discussed, right? That is because this itself. Simply take a matrix. Yes, any number of column doesn't matter, right? I said that in a real-time data you may have 100 columns. Doesn't matter. Now you see, simply take a matrix, take its transpose, x transpose, multiply that with x, your original matrix. Take a inverse. Okay, you get something, multiply that with x transpose into 1. You get the theta directly, because the how many number of columns you have, so many number of thetas you want, right? You get that. So this is a direct answer, right? So those who say that no, I don't want any method, directly show me the answer. This is the answer. So in the sense, if you want to perform a linear regression, you have to do this mathematics ultimately, so that you find out the various theta naught. Your parameters are directly available. Put it into your equation, form a straight line, and put the various values of the columns of your data set. You will get the approximate close answer for that is y cap. Very simple. So this is linear regression. Now you say that no, this is so easy. Why the complex name is given like linear regression and so, right? We'll come to that. There is a name in the literature. If you find various references, it says that this is the normal equation. Very important. Let's remember this term. Okay.
So what is the meaning of MAC? MAC क्या है?
Mean squared error. Okay. I'll
Okay.
just go back to make things clear, so that let me write the word, so that when you refer this notes, you should be in a position to understand. Okay. So this is the top one is mean absolute error. Okay. So this is mean square error. So in this part, I don't see a mean, right? What you are supposed to do for mean, the mean has to be calculated by taking a summation and dividing this by the number of entries, that is n. Okay, so that is there, but in order to do that, anyway, squaring is required. Okay, so if you use a squaring over there, that becomes a squared error. Sum of that and divide by the number of items, you get the mean. Same thing happens here. There is a sum divided by m is required, number of entries you have. Okay, so anyway, right now we are not writing that part. Just understand that the term which is important for calculating MAC is a square difference.
So
Okay.
in the first, in this particular section, the first equation will be the y naught minus y naught, or y naught minus y.
Which one? What's the first equation? You mean to which one? Which
So
equation?
where not
This
equals to error.
This
error
one?
you have-
Y
This-
naught minus y
Yeah,
should be right.
Yes. Thank you for correcting me. Yes.
I'm not
Yeah,
correcting.
that's
I'm
right.
just
No.
confused.
I made a mistake, right? So thank you. Yeah, it should be y cap minus y. Okay. So if you write y naught cap, it is y naught cap minus y naught, right? So y is the actual value, y cap is the predicted value. So difference of that is what we are calculating as error. But as of now, we understood that under this scenario, we cannot use that, right? Yes. Any other note? Okay, so till here, fine, I guess, right? So this is the easiest one. Even if you don't want to go in depth about the mathematics behind that, absolutely fine. You understood everything that is required for linear regression. Directly, we can jump into the programming as of now. But anyway, I'm not going to do that. I will deal with the mathematics. Those who feel that, okay, this maths looks pretty tough for me, now you know that, okay, that doesn't matter. Anyway, I have the answer with me, right? Okay, so before going to the maths, let's look at what exactly is happening in case of the linear regression models. After this, I'm jumping into the maths behind that. All right. So in case of the linear regression, right, what we are trying to do, our intention is to predict something. What you are trying to predict the value of some continuous variable But in order to do this prediction, there is a supervision that is required. In the sense, for these x1, x2, x3, sorry, for these x1, x2, x3, x4, this is the curve. For the next set of x1, x2, x3, dot, 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 this is the curve. Like that, I have to teach. So that is a supervision, right? So I can write a continuous variable in a supervised settings. This is very important. I have to have a so collected data is required. Okay, without that, this is not possible. So what is my equation? I'm trying to write it again so that everybody becomes comfortable with this representation. What you are trying to do, I'm trying to make a prediction y cap h theta of all the values of x. Now you see this x is capital, indicating that this can be a vector x1, x2, x3, dot, dot, dot. And I need a parameter to be defined, that is a theta. Okay, so now I'll come to the technical details where the h is what is called as, can anybody suggest what is this h? We have actually used this starting from h.
Function?
No, a word starting from h we have used many times. Recall statistics. In statistics, what was the term we used many times? What testing you did?
Hypothesis.
Yes, this is hypothesis. Okay, so h is the hypothesis, and yeah, theta is the parameter, or I can call it as a ML parameter. That makes more sense. All right. So, how do you calculate the theta? Right, I already have written one equation. You will say that machine has learned something, means I have to minimize the error, right? Minimize the loss function, right? So I can say, I'll write one very important sentence, right? The theta can be, you are actually, theta can be learned, right? You are learning theta now. Machine learning in case of this linear regression is what? Learning what is the optimum value of theta. So what you are learning in linear regression, the theta parameter is what you are trying to identify. You can say that I am estimating that, I am calculating that, because the above equation, the matrix equation I told, right? Theta can be directly calculated using the normal equation. There you are actually calculating, right? So that's a standard equation, but that equation comes from some calculation itself. All right. So I would prefer saying that you are learning that theta value, right? By solving the optimization equation. What is that? I am supposed to minimize for all the values, that is j is equal to 1 to m, because j1, j2, j3 up to jm, m number of rows I have. For each one of them, I am supposed to perform the yj cap minus yj whole square. This should be minimum. But as you know, this is not a mean, this is simply squared error, sum of the squared error. If you want a mean, just multiply by 1 by n. Okay, so I have to minimize this term, for which the theta is called as the optimized theta. I hope this is clear. Let me know if you have any doubt up to here, right? Including the equations or the concepts, anything you have, please go ahead. Because next I'm jumping into the derivation part.
Sir, could you go up a little bit?
Yes, sure.
Down, sorry.
Down. In a sense, this is the last equation I have written.
Yeah. What is the, sir, you can explain this LR.
Yeah, which one? Sorry, I didn't get.
Go down, sir, go down.
Down, further. No, I think you mean up, right?
No, down, sir, down.
LR, this is one. In LR means in linear regression.
Yeah.
In case of a linear regression, so what you are trying to do, we are trying to predict the value of a continuous variable. That is my count. Bike count is a continuous variable. Okay, I am predicting that, given that x1, x2, x3 various parameters are given, And also there is a value of y is also given. For these set of values x1, x2, x3, this is the value of y. I have to predict that y which is close enough, right? Prediction is y cap. Y cap is close enough to y. This is what is our problem definition. So that's what is the meaning of that particular sentence. Mathematically, you can write as that equation. Y cap is equal to hypothesis of theta given the x parameters, finding out the theta. Okay, so that is what is about this, where h is called as hypothesis, theta is the machine learning parameter which you are supposed to learn. Okay, is that fine?
Yeah, got it, sir.
Sure. Any other doubt? So this is the fundamental idea, right? In short, whatever we were discussing in the past 1 hour, I try to club it all together and put it in a single 2 or 3 lines in the previous page. Okay, you can refer that. That becomes very clear, right? When you read these notes, things will be very clear for that. Okay, now let's go to the mathematics behind that, right? Some of you may feel that this is I'm not understanding this. This is too difficult. No problem. Okay, so once you get these notes, do the maths by yourself, step by step, right? So that you may be comfortable with that. Okay. Otherwise, as far as the knowledge of the LR is considered, right? You don't have to know this derivation at all. Nobody can expect somebody to do this derivation. Absolutely not. Okay. So even I'm going to make it as compact as possible. I'm not going to do the complete derivation, right? In the middle, I just said that this is what is happening and I get this. Okay, so something like that I'm doing. So my requirement now is, right, okay, this is my problem. Y cap should be equal to theta 1 into x1 plus theta 2. Okay, capital X1 indicates that this is a vector. I'm not going to write that. I'll write just x1 here. Okay, x2 plus okay, I'll make things more clear, more easy. Let me remove the theta naught also. Fine, let's because I just want to know the maths behind that. Ultimately, I'm going to write everything in the form of a matrix, right? Sorry, if you want, you can simply add the theta naught to matrix and add 1 to the new column. Anyway, you know that already we have done that. Let me make it more easy. I'll remove the theta naught. Let's say that there is no theta naught and theta naught equal to 0. This is what is my question. I have to find out I have to learn the theta 1 and theta naught, so that I can write y cap is equal to capital X into theta. Capital X is a matrix, you know, theta is the matrix consisting of all the parameters. This is a column vector. All right, so I will start calculating the loss for the theta. That is, I have 2 theta values, theta 1 and theta 2. So how do you calculate that? Let me say I have 3 rows in my matrix. Let me make things very clear. Let me make it easy also. So what I assume, I have this is my data set. Data set has 2 columns, x1, x2. Definitely I have a y there, but for training purpose, I use y as a target value, right? So let me say there are 3 rows only. Okay, this is 1, 2, 3. So because of this, now what happens? How do you calculate the loss? This is y1 cap minus y1. So I'll call this is y1, this is y2, this is y2. So there will be a prediction that is happening, that is y1 cap, this is y cap, the next column which you can try to add over there. So you just see that this is y2 cap, okay, and the prediction is y3 cap. I hope that is clear. So let me slightly move to the right so that you can see that. All right. So this is the L value which we are trying to calculate. This is y1 minus y1, y1 cap minus y1. I'm going to stick to this square notation. So that is the first term, plus this is y2 cap minus y2 whole square, plus this will be y3 cap minus y3 the whole square. So so far everything is fine. Anyway, I know that I'm making a new column for error where I write y1 cap minus y1 whole square. Since you are squaring, there is no question of negative term. I want to keep the whole sum as minimum as possible, isn't it? Okay, now you expand this. Okay, what happens when you expand this? What is y1 cap? If you remember, y1 cap is nothing but theta 1 x1, right? Because I can call this is, okay, let me write it in this way. This is x1 1, x2 1. This is, right, x2 1, like, my mistake. I cannot write that. Okay, this is x, just a second. I'll make a correction. So this is again x1 second, x2 second, x1 third, x2 third. Okay, so those are the different values. Now, if you remember, theta 1 x1 plus theta 2 x2 of the first one minus, this is the same term, y1 square. Okay, plus, now as we proceed, things may tend to be slightly complicated. Don't worry about it. Okay, so I'll just tell you the steps so that you can work it out by yourself in when you have enough time, right? So the second term, what happens? This is theta 1, and my next term comes into picture, that is x1 second term plus, this is theta 2 x2 second term minus the y2 square, isn't it? Then the third term comes into picture, plus theta 1, this is x1 third term plus, this is theta 2 x2 third term. Okay, the cube, it's not a cube. Okay, so if you are confusing, please put a bracket around that, just to make sure that, right, you are not considering that as a cube. As far as I understand what I'm writing, you don't have to make things complicated. Okay, so this is y3 squared. All right, so what is going to happen next? I'll skip a step. You can actually square this and you can write a lot of mathematics, right? That's going to come, right? I'll skip that step, right? What I want is, I don't want to go to the simplified answer here, but I want this to be minimum. So under what condition this is going to be minimum? You have to calculate a gradient and you have to equate that to 0. So that is what is this. Differentiation of that L with respect to theta should be equal to 0. Correct? So anyway, I have two different theta 1 and theta 2 present. So I cannot differentiate this directly with respect to both of them. Again, that is the fundamental requirement, right? Fundamental condition that we are taking from the differentiation, the calculus part. So what we do, we'll do step by step. So what we are going to do here, look at this equation. There is L. We do dou L by dou theta 1. This is called as what? This is called as a partial differentiation, right? Those who are not aware of this, right, you may have to go back and you may have to study that and come back. Okay, it's a partial differentiation. So when you do the partial differentiation, what happens? I'll just write the required answer directly. Okay, so this is, so there is a square, right? So 2 times, you get something 2 times. What is that? Theta 1 x1 plus theta 2 x2 minus y1 into, right, I am differentiating with respect to theta 1, so only the term containing theta 1 comes out, so that is x1. Next term, so similarly you write the other terms, plus 2 times the second term, that is theta 1 x1 second term plus theta 2 x2 second term minus y2, there is no square, right? And you are going to multiply that with what? Whatever term containing the theta 1 here, that is x1 second term. Okay, so just let me move, right? So this is the complete equation. Then I'll do the with respect to third one, that is plus 2 times theta 1 x1 third term. Look at the table if you want, where is this term coming from? Okay, so that is theta 2, this is x2 third term minus, this is y3, no square, multiply that with x1 the third term. I hope the differentiation is straightforward, right? What I got is only the differentiation with respect to, right, this term, that is dl by dou L by dou theta, right? Those who are interested in mathematics, I want you to do the next step. I'll leave this blank. I want you to calculate dou L by dou theta 2, right? You get 3 terms, 2 times something into, this is x2 of 1 plus 2 times another term, This is x2 second term plus 2 times a term into x2, my mistake, this is 2, the third term. You get an equation in this fashion, right? You can directly do that. Now, what I'm trying to do here is using these two equations, I can convert the two equations into a matrix form. For that, we need the basics. Again, the basics are directly collected from the linear algebra concept. Okay, linear algebra says that if you have the dou L by dou theta for different values of theta like this. So equation number 1, dou L by dou theta 1. Equation number 2, dou L by dou theta 2. If you have these two equations, right, I can definitely go ahead and I can modify, I can convert this equation into the following format. Okay, so that format is what I'm trying to write now. Okay, so let's try to write that. So this is how it's going to look like. So the equation is, I'll write a next answer. So if you want, you can fill this out. So I'll directly write this. Dou L by dou theta 1 is my first equation. Dou L by dou theta 2 is my second equation. So this I put as a result in the form of a column vector. Okay, so that should be equal to, what it has to be? It has to be equal to 0, right? Because theta 1, theta should be optimum only when this results in zeros, right? So in order to do this, if you want to look at the, what you call, right? I'm actually skipping one step. You write dou L by dou theta, you write dou L by dou theta 2 equal to 0. You get a matrix format. In the matrix format, I have to take something common. So what is that common? That common will be this x transpose into x theta minus y. This is what you will be able to observe. Okay, so that means I can directly write that. This implies the x transpose into x theta minus y, that itself equal to 0, correct? So because I can simply expand this x transpose x into theta minus x transpose y becoming equal to 0, or in other words, I can also write this is x transpose x theta equal to x transpose y. This itself is another form of our normal equation, right? So earlier I wrote a normal equation, right? So from this I can actually take out the what you call as the theta. How do you calculate theta? So theta is equal to, take this to the other side, that makes it x transpose x inverse into x transpose y. So this is what we call it as a normal equation. But anyway, so the steps are like this: calculate the partial derivatives, convert them into a matrix format, then simplify, you come to this. Okay, so this is what is called as normal equation. So far, we were discussing about the linear regression, and in order to learn the parameters theta, we have to use what is called as a linear equation, and the specific format of the linear equation, which we are going to see, that actually we have derived, right? You can see that it is in the it's as visible on our screen. Theta equal to x transpose x whole inverse into x transpose into y. Okay, so this is the straightforward implementation. You can simply write this equation. You can use say numpy for taking a transpose and multiplying np dot, right? Doing this, taking a inverse, etc. Everything is possible. Go to the basics of numpy. You can definitely do that if x is a simple array. But for the implementation purpose, we have to go to a specific library. Okay, so that is called as the scikit-learn. It's a library that supports most of the machine learning components, right? You can call the built-in functions directly so that you can implement whatever required. So in short, this is called as, okay, so short form is sklearn. All right, so it's a short form. Okay, now I'll write a part of the code if you are using the scikit-learn for the what you call as if at all we are going to use it for the purpose of say linear regression, right? We will be using the following code, right? Maybe with small modification, right? So we have to import that. So this is the code. When we actually write the code implementing or solving the problem which we had defined earlier, definitely you can see the similar code is going to come. So first you need to import some, right? So the first line of the code will be from sklearn dot okay, I'm not going to a part of it. I'll directly from sklearn I can import. See, all the regression which are falling under the linear part actually is present inside a model called as linear underscore model. All right, this will be my first line. I'm actually importing the complete class of say models which are linear. Okay, so that's one thing. So I have to create an object first. Okay, so this will be your model, right? So I can write it's a name. You can give any name. Even my name will work here. So I'll write linear rig. So something which is not a keyword, you can use it here. So this is equal to it's actually present inside the linear underscore model. I have to call dot linear regression. All right, so linear regression, I'm saying that I'm creating an object. The name is lin underscore re. Right. Then I have to fit the in the sense it actually calculates the values of theta by using the required equation. All right, so that is lin rig dot fit. You are trying to fit a curve, right? So you are trying to fit a required equation. So dot fit. So I'll be having I'm coming to the splitting part after some time in today's discussion, maybe after 10 to 15 minutes. So you will split your complete data set into training data and the testing data. Okay, so out of which you will have let me call it as x underscore train. That part of x matrix which I use for training is x train, and the same part corresponding to those x I have some y, right? I'm going to call that as y train. Okay, x train and y train I pass, and I'm going to ask the machine to fit a linear regression, fit and learn the machine, do the machine learning. So that is what is happening here. Once machine learns the values of theta required to do the prediction, right, you can do the testing. So how do you do the testing? I'll calculate what is called as y predicted. So this is what machine predicts, y cap, what we written. Okay, y cap is equal to the same model, lean reg. This is the model which I have trained now. Okay, it's present in by this name, lean underscore reg. I am asking the machine to predict. So this dot predict is a function. I will pass x test. So what is x train? What is x test? X train is the training data. X test is the testing data. Details will come shortly. Okay, in today's session itself. So I have this. Now the y predicted is the y hat. Okay, after learning and obtaining the what you call as optimum theta values, we are using that. Now, how do you look at the theta? How do you find out that yes, I have an answer? Okay, so you can write maybe. So I can simply print the model name lin underscore reg dot interce intercept. Okay, intercept underscore is there. It's a inbuilt method just to because if you have created a variable by name intercept, that should not coincide with the intercept of this machine learning. So intercept underscore is there. That is the built-in way to distinguish. Okay, so Python distinguishes. It's not the intercept which I may create a variable. It's not that. It is the intercept of this machine learned concept. then LIN_REG, linear, that's the model, dot COEF is a coefficient. Theta 1, theta 2, theta 3, they are the coefficients. And the theta naught is the intercept. Okay, theta naught comes first, then COEF again underscore. Okay, so again, you might have created a variable by name COEF. So the Python wants to distinguish between that and the one which is printing. Okay, and also if you want, you can have the predicted value. You can even print this. This is optional. Okay, print LIN_. Okay, it's not a part of this. It's just a variable. Sorry, you don't have to do this. Simply go for Y predicted. If you want, you can print out. So this is a rough code. Okay, so what I want you to do is, I want you to search the documentation of sklearn. So just note down this name. Anyway, you are going to get this material, and even you can even do that. But let me show you that. So right, sklearn is the short form for the scikit-learn, which is a very powerful and important library in Python that supports most of the machine learning techniques and the functions as well as the models required for ML. So very important, but teaching that is not a part of this course, so I am not going the details of that. We are not going to discuss each and every part. This is how the data set works, etc. We will not be discussing that directly. We are using that, right? So general architecture I already mentioned, but anyway, that may not be sufficient for everyone to understand. So I want you to find out the documentation. Just search sklearn documentation in any website. You can search and you can find out a documentation, and general way, whatever is required, you will find over there. Okay, go through that just to make sure that, okay, this is how the flow looks like. Normally you have to split your data set into training and testing. Then you import the required inside the scikit-learn, whatever is the import model that you want to import. In this case, I imported the linear model. So if you are going for any other model, you have to import that. Then create a object by any name. Okay, so LIN_REG is what I have used here, right? I created an object, fit the object, that means training, do the testing directly. 4 lines of code is there every time. Okay, but importing which model, where is it located, what is it called, what is the name, etc., you need to know. For that purpose, I am asking you to refer to the sklearn documentation available in the internet. Okay, so save that link, whichever you get. Yes, scikit-learn website is there. You save that, okay, with you, and whenever required, you can go there and you can check. There is also a search button. If you want to go to, say, Navy base, you can simply search Navy base. It will give you the help how to use the Navy base and the sklearn, etc. So that is the fundamental requirement. So before we go to the coding, mostly that's going to happen in the next class. So I want you to just go through with and get ready with the way of writing the code, right? That's the first thing. All right, and let's move further. So this is the rough code. Anyway, we are going to write this code in a file. We'll do the programming properly. Okay, but just to give a hint, what will be the code, how it is going to look like, I have written something like this. All right, so now, yeah, so that was the first thing which I wanted you to do. Let's move ahead. Let's go to the next part. Whenever we observe the data, there is a possibility that a particular column is correlated with another column. In a sense, maybe when the temperature increases, there is a possibility that one more column is also going to increase, not Y. I'm not talking about Y. Don't consider Y at all. Y is a prediction method. Okay, Y is eliminate the complete Y. I'm talking only about the X matrix. In the X matrix, there is a possibility that Y, a particular column, is actually correlated with another column. One increases, other one also increases. There is a high correlation. We say that one decreases, the other column also decreases. This is possible for multiple columns. All right, so this is one very common problem. So as far as our intention is just to make a prediction, in the sense, use all these X values and you predict something. Okay, as far as our intention is just to make a prediction, not a next level of analysis. What is the next level of analysis? I'll come to that. So my intention is use all the data in X, make a prediction of Y. If that is the case, this correlation which I mentioned right now, right? That doesn't matter. No problem at all. You will be able to do that. This is, I'm telling from my practice. Okay. When there is a high correlation between the columns of the matrix, X matrix, that is a data set which you have, right? If your intention is just to make a prediction, no problem. Absolutely fine. But if you go to a next level, what is the next level? Like which column highly impacts your output, that is Y, which is the most important column that actually is a main part in the decision of the Y value, then this particular problem, that's called as a multi-collinearity. Okay, it's called as multi-collinearity whenever multiple columns are actually highly correlated, right? If that is a problem, then there will be a problem. Okay, so but anyway, what we suggest is that irrespective of your problem, you try to nullify that effect. Okay, so the nullification of that can be done using the following technique. Again, this is useful, may not be very useful in our problem, but I highly insist you to know this. Okay, that's why I'm talking about this. Let me write a point here. This is called as, I write the name. The columns of X are correlated, means that is a problem, right? We call it as multi-collinearity. All right, it's called as a multi-collinearity. So I'll repeat, if you are simply predicting, no problem. But if you are doing an analysis saying that which of these columns is very important to predict the value of Y, something like that, if that is your analysis, anyway, we are not doing that in this particular concept of linear regression, but in future, somewhere you want to do that, means, right, this is the answer. Okay, so what you will do, you will perform. So you can make the following step, you can include the step in your code so that you can eliminate that effect, right? Collinearity, whatever is there, you can try to modify that by doing this. It is called as do the standard scaling. So what do you mean by standard scaling? Very simple. Remove the mean from column. I have a column. Calculate the mean of that column. From every value, you subtract the mean. Where you have seen this? You have seen this in the normal distribution, X minus mu. And what you do? You divide by the sigma, correct? But as of now, you don't have to divide by sigma. Okay. So remove the mean from the column. That is what is called as a standard scalar. So from, you see that there is a mean value for each of the column, you remove that. Okay, so that is what is called as a standard scalar. Again, you don't have to do this column by column. There is a built-in function called standard scalar. I will show you that. Okay, when we write the code, I'll definitely show that. But remember that there is a concept called as standard scaling. So I can say that use function called standard scalar. It's present in the sklearn, scikit-learn. Directly we can use it. All right. So that is one more concept which I want everyone to remember. Right. So why do you need standard scalar? Whenever I fail something, some issues with the columns, they are highly correlated with each other. I can deal with that by doing what is called as a standard scalar, right? Which eliminates that or nullifies that particular effect. Hope it is clear. Any doubt? All right, so let's move further. So this is actually a part called as the train, test, split of our data set. Very important concept. Now, what I try to do here is I have the complete matrix. Let me write a matrix. I'll not write the details like whatever I wrote earlier, but I'll just try to denote what is there. So my last column is Y. Okay, this is the Y. And I have many X columns over here. So let me write few of them. X1, this is X2. Like that, we have many columns coming up. Let me say the last one is, as I told, that is Xn, n number of columns. So I have many rows here, R1, R2, dot, 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 etc. Okay, so this is the representation of my data set. Now, what I'm supposed to do, normally, the data set will be split into two parts. Okay. Again, there is a thumb rule that says that you will select 80% of the data set for what is called as, we'll split it into two parts. Okay, let me write that part first so that it becomes clear, right? Let me split it somewhere here, showing that this is the 80% data. Again, this is a thumb rule. There is no, nobody will raise an issue if you split it to 70-30, no problem. Okay. Thumb rule. Most of the references say that do this, it works. It will definitely work even if you do 85-15. Even if you do 90-10, it will work. Okay, no restriction, just a rule of thumb, that's all. Okay, now the 80%, the majority is what is called as the development set. Okay, development set. Training, we will come to the training part later. Okay, so the majority of that, 80% or 70% as per your preference, it's called as a development set. Then the remaining 20% is what we call as a test set, testing data set. All right, fine. Now, actually, we have another part coming. Out of this 80%, I'll go down, I'll go to the next. So the splitting is fine for you. So how to do that? How to do splitting? Again, we have a built-in function. No need to worry at all. Simply say that I want 80% as a training set, development set, it will put into that. Okay, absolutely fine. Nothing to worry. Built-in function. Okay, but you need to know something about this whole process. That's why we are actually spending some time over here. Again, this is the first concept under machine learning. So we will be discussing this in detail. Later on, we'll never touch this any further. Okay, so because you'll be familiarized with this whole process again and again by writing code several times. Okay, so now you see we have what is called as a development.
Sir,
yeah,
please explain once again table. My internet is slow, so I.
Yeah, sure. So we actually have the complete data set. We divide the data set into two parts. One part we call as a development set. The second part is called as a test set. So normal rule is that you take 80% for the development set, remaining 20% for the test set. Okay, so this is what is the splitting up. Again, we have a built-in function in sklearn. We'll use that for this purpose. Okay, then we have something more to discuss about the development set. Test set is absolutely fine. Once I split it, I think that this test set does not exist at all because I'm doing the training. So once I do the training, then only I'll ask the questions to the machine saying that how much you have learned. It's like our exam process. Like I take so many classes. Okay, and at the end, right, once the training is complete, you will go for a testing phase. I ask many questions to you. You have to answer. Maybe it's an exam, it's a coding test or something like that. So it's the same process. So whenever I'm doing the training, you will see that you will never see what are the questions that are going to come in the exam. So this is the same process. Okay. So the idea is that you will never see the test set during the training. Okay. Now I have splitted that. 20% I have removed from my X table. It is completely kept separate. It's not at all available. So it's called as a data leakage. If you make sure that if you keep it with the same variable, maybe there is a chance that the machine knows what is going to come in the test. So what happens if you know the questions in hand before the test, means that's not a valid test, right? So because of that reason, we keep the test set separately. That's why the train test split happens. So 80% is a development set. Among the development set, we have to have two different parts. Okay, so the one part is what we call as the training data set. Okay, and the second part is called as the validation. Okay, so what is the training? What is this validation data set, right? In order to teach the machine, we will give the data one by one, right? So that itself is a training. But why do you have to split the something separately and call it as a validation data set? So it is something like I teach you something, and in the middle I put a quiz, correct? I put a quiz in the middle saying that, okay, I just want to know how much of whatever I taught you understood. It's not actually a test. It is something like just validating that, okay, whatever I have learned, whether you understood or not. So that is my point. Same thing happens here. So that particular concept is called as, in machine learning techniques, it is called as remember this term, this is called as k-fold cross validation. Very important. Okay, k-fold cross validation. What is this k now? I'll come to that. Let me consider my table once again, but right now I'm considering only that part of the table which I have split as the development data. Okay, this is the 80% of the data which I already have separated. No test data included in this. Okay, so let me assume that I have say 1000 rows in it after separation of the test data. There is no test data in it. It contains only the development data. Now what I do, let me say k equal to 4. This k fold is there, right? I'm taking k as 4. Again, simplicity, the standard value, if you don't mention k in your program, scikit-learn takes k as 5. Okay, anyway, you can specify, you can say 10-fold, you can say 15-fold. Standard value is 5, that's all. No harm if you use 2, 3, absolutely fine. If you use 10, that also is going to work. Okay, standard value is 5. For simplicity, I wrote k equal to 4 here. That means your complete development set will be divided into 4 pieces. Each piece now contains how much? Because that's why I took a easy number like this. This is 250. This is 250, second piece. This is 250, third piece. This is the fourth piece, 250. So let me say this is 1, this is 2, this is 3, this is 4. 1 means first piece, 2 means second piece. It contains 250 rows. Third contains another 250 rows. 4 contains another 450 rows. Now, what do you mean by k-fold cross validation? So k-fold cross validation means there will be training that is going to happen k times. K means 4 in this case. So why 4 times training happens? The complete data set what you have, right? That will be used for training k times. Why k? This is the answer. Okay. So what happens? Every time the machine gets trained, there is a theta value that it generates. Correct? Because ultimate idea is to calculate a theta. Right. So first piece goes into the machine. Right. So this is how it happens. I'll just write the first, the second, and the third. First 3 pieces will go to the machine. Machine gets trained. Every time 250, 250, 250. And machine generates a specific value of theta. Okay. And you will validate that, because I have to validate whatever I am teaching you right now. I will ask a question, right? Maybe a quiz, so that I'll come to know that what is your understanding of what. So same thing happens here. You validate with the fourth set. Fourth set is not used for training. Though you divided 1000, you separated 1000, out of which 750 will be used for training, remaining 250 for validation, like asking a question, just to know that no training happens, just an estimate, like out of the 250, maybe 200 are properly estimated. So there is a error of 50 are not being classified. So once again, training will happen. So in the second time training, you see 2, 3, and 4 will be used for training. The first set will be used for testing, not testing, sorry, validation. It repeats. Now I told 4 times, right? This is the 4 times. Then 3, 4, 1 will go to the training. The 2 will be the validation. Then 4, 1, 2. Then this 3 will be the validation. So you see, this is why I told the training happens 4 different times. So k-fold cross validation means this, right? So this is train, this is validate. So k-fold, k times happens. That's why this is called as a k-fold. Normally this k value we need to enter. If you don't enter, it is 5. Okay, the whole data set will be divided into 5 pieces. 4 of them will be used for training. The 5th piece, right, will be used for the validation purpose. So this is repeated 5 times. So you have that answer coming into picture. Now, why do you do that? Why should I use 5 times? Why not only 1 time? What happens? What's wrong with that? So the answer is that every time you get a theta star, so theta star for the first one, theta star for the second one, theta star indicates optimum value. So theta star for the third, theta star for the fourth, right? Out of them, whichever is the best value, right? All of them, if you do in a single step, you may not get the correct answer, right? So you see, actually there is a shuffling that is happening. 1, 2, 3 is given, 4th one is validating, 2, 3, 4 is the one is the validation, 3, 4, 1 is the testing, second one is one. You see, actually some shuffling is happening, right? So again, this idea has been suggested by doing a lot of research. Okay, not somebody simply gave an idea that everybody is working that. No, a lot of research has been done. You can refer the standard journals or standard publications to understand more about this. Okay, why the k-fold cross validation is widely used? Because people have done a lot of research and they accepted that yes, this is the one which gives you the best possible solution. All right, so because of that, yes, so k-fold variation will be done. And out of the so many theta stars you get, right, for each of the time you train and validate, whichever is the best one, you will choose that as your final answer. Okay, so I hope that is very clear to you. Any doubt with this? Please go ahead. Okay, good.
Suppose, hello.
Yes, Devendra. Please go ahead.
Yeah, yes. Here actually, 4 times we are doing training, right, sir?
Yeah.
So whatever theta value, star value, come minimum, that we have considered theta value.
Yes.
Right.
Right.
Okay. So suppose instead of 4, if we take like 8, then chances of getting more accurate value, theta value, chances increase.
It's not like that. Again, actually that depends upon what data set you are having, what are the features you are. It depends on many parameters, but the research says that ideally people choose 5 as a standard one. So, right? Again, there are some cases when you use it as 8, 10, some chances are there which improves your performance, but not by a huge margin. Okay, maybe slight increase is there. Okay, so that's what people have observed from doing a research. Okay, may not be always.
Yeah. Okay.
So one question.
Yes, go ahead.
That as you said that 1, 2, 3, 4 will be the testing, and we get the theta star from every row, right? From the every fold.
Yeah, every fold. Yes.
Right. So can we see that what's the value for the first one and what's the value for the fourth one? Because the computer will automatically give us the minimum value, right?
Yeah, best
But can we see
value
the
will be chosen.
other values as well?
Yeah, you have an option. If required, you can extract that out. Okay.
Okay.
Sure. But since our intention is selecting the optimum one, most of the time we'll never care about what are the other values. Only the optimum value will be extracted and you can use it. But yes, you can write a code, you can modify that to get what you need. All right. Yes. Okay. So the next part is we'll slightly move ahead. Yeah, we have another question. Yes, good. Yes, go ahead.
So sir, this way we can find theta value, right, sir?
Yeah. Correct.
This is a method of find out theta value that we required for machine.
Yes. Theta are the parameters, right? So what are the parameters? Optimum for your particular problem, we can find out like this. So k-fold is used to improve your theta. That's all. Okay. There was a concept called as previously we discussed that optimization. How do you optimize the theta? How do you select the proper theta? So this is one method that is called as a k-fold cross validation.
Basically, still we are working basically like finding out the ending point.
Yeah, correct.
Right, sir? Yeah. Okay.
Perfect. Okay. Now,
but sir, this theta value will be just for 80% of the data.
Yeah.
Right.
80% of the data is considered for the training and the validation. Okay.
Okay.
Remaining 20% you will keep aside. You are not using that.
Okay.
You will never be using that because you have to ask some questions, right? If you keep everything, if you teach everything, right? What is there to ask question, right? Nothing. So you keep it aside. Right. That always is not. I initially mentioned that you think that test data does not exist now. Completely removed from your data set. Completely keep it aside, right? Okay. Right. Now, fine. Let's go further. Now, fine. Let's say, I think this concept we actually have, I brought it once, maybe in the, I think yesterday's session, in one of the slides, the word came into picture. Now I want to discuss that slightly. Okay, so this is what is called as the minimization problem, because I want to minimize the theta. Sorry, minimization problem. I have to minimize what is called as a loss, right? Because loss has many versions. One of them we have chosen, that is a mean squared error, right? So now let me try to draw something so that we can elaborate what exactly is happening here. So this is the theta values. Let me take only one of the theta, not all of them. All of them I cannot plot because every theta is different axis. Theta 1, theta 2, theta 3, theta 4, like that. If you draw that, it becomes a multi-dimensional case. Visualization is very hard for human beings. If at all, it is a multi-dimensional case. So let me stick it to only one. So there is only one theta to be found. I will call that as a theta 1. In the sense, there is a x value, there is a y. For every x1, y, x2, y, x3, y, like that. You have to simply find a equation for relating x and y. That is what is the regression problem right now. So what we do, along the y-axis, let me calculate and plot the loss corresponding to this, the loss or the cost function corresponding to this theta. Normally what happens, this could be a curve something like this. Let us see. I'm considering the simplest one just to make sure that everybody understands. Okay, it can be a complex curve as well. Let me assume that this is how it looks like. Now, whenever you start your training process, maybe it starts from this point. Okay, so this is the point from where it starts. Where do you want it to end up ultimately at once you finish the training? I have to reach this point, correct? So this is some initial value of theta. I can call it as, say, some maybe theta 1 first value. After the training happens, the theta 1 reaches a second value. Like that, this is the value where the theta reaches optimum value. Theta star comes at this point. At that point, if you measure the loss, this is L of theta 1, which is the minimum value, isn't it? So this is the minimization problem. We call that as an optimization problem initially. I want to minimize the theta How did you do that? Already we have done the maths behind it, but I wanted to show you this using the pictorial view. What exactly is going to happen? Again, I consider a simple example of a one-dimensional case. So you start with some loss or the cost, which is very high. Gradually you need to decrease and you need to reach the minimum possible point. So that's why we did dou L by dou theta and equated that to 0. So if you try to calculate the slope here, the slope is 0, right? It becomes a horizontal line here, so that the slope is 0. Again, everything is coming from analytical geometry. I'm not going to touch that one. Okay. Now, so in another view, this is a different view. Again, the technical term comes into picture. So the technical term that we are going to use here is called as, this is the word we used earlier. This is gradient descent. So you calculated dou L by dou theta. Depending upon the dou L by dou theta, the theta values will change such that the dou L by dou theta becomes equal to 0. Right? So this is what is the concept. This is what is implemented by using technical term, and the algorithm that we are going to apply is called as a gradient descent. Okay, now I'll come to an example. Just assume, right? Assume that you are at the top of a hill. Okay, you went for hiking, you reached the top. Absolutely fine. You enjoyed. Now you want to come down. Okay, again, we'll put a condition that you have to tie your completely, right? Tie your eyes, you cannot see, right? Without seeing anything, you have to come down. This is the condition. What we can do, again, I'm giving a solution with which is pretty much similar to what is happening with the gradient descent. Okay, so right, you cannot see, so eyes are tied. What I do, I'm actually, this is the tip of the hill. I'm standing there. I'll rotate once with my legs touching the ground. I rotate once completely, saying that which part, because I want to come down as quickly as possible. There is another condition. You cannot spend the whole day identifying which route I should go. It's again not possible. You have to reach the bottom of the hill as early as possible, because I start from this point. I have to come down as quickly as possible to the minimum point, right? I cannot keep wasting the time by moving slowly. Again, that is not possible. Computer is going to take a lot of time if you allow that. So I want to reach to the bottom as quickly as possible. Plus, I cannot see. This is the physical condition that I'm going to put. So what you do, right? Once you completely take a 360-degree turn, right? You will observe that which part of, when I rotate like this, I try to identify which part of the hill, right, is actually more steep. I'll try to find it, because if there is a more steep, I can actually go down faster. This is the idea, right? So I try to rotate in that way, right? And I'll identify that, okay, this particular direction has more slope, and I can go, if I go there, I can reach the bottom quickly. So same concept is what is happening here. Now I'll write an equation justifying this. Okay, so this is the objective. I find out, okay, this is the direction in which I am supposed to go. What do you do? Whichever is the best step size possible from your side, because depending upon the height of a person, the size of the step varies, correct? Maybe somebody may put a step of, say, 1.5 feet. Somebody may use just 1 feet. Somebody else may use, say 2 feet, or variations with that. According to your suitable step size, you take one step. Again, in that point, you will make because you may have to slightly change your orientation. Right now, I was moving in this direction. Next step may be slightly on this direction. Next step, slightly this, because you have to make a survey once again. Slightly observe that with, since your eyes are closed, you cannot see which direction I'm supposed to go. But this is the most suitable way to reach the most bottom point. In the sense, once you reach the right down path, so wherever you don't feel any slope further, you will consider that as the bottom of the hill. Right, so that is the concept, right? Again, we neglect that abnormal shapes of the hills, etc. Just neglect for the time being. Just consider a shape which is pretty much similar to this graph. You are at the top, you want to come down. So same thing, whenever we try to apply that, right? This equation. I'm going to write an equation now. This equation we are going to see n number of times now onwards. So that equation is the next theta value. So theta k plus 1 is equal to the current theta k minus, this is eta k, into the gradient of, I can write L of theta k. Now this is the equation. I'll tell you what it is. Now theta k plus 1 is my next value of the theta. Okay, above you consider the above graph. Okay, the next value of theta, right, is decided by current theta, that is theta k. Again, it says subtract because I'm coming down, subtraction. The eta, the n, what you see there is called as a learning rate. Learning rate is equal to my step size. Whatever I am comfortable, I can choose, right? So learning rate is normally kept between 0 and 1, right? There are many other versions also there. We'll discuss that at the right time. So just relate to the problem which I discussed. So this theta k basically is, this eta k, it's not n, it is eta. Okay, eta k is the learning rate, right? I'll just write, this is called as learning rate, and this del is nothing but this is the gradient. That is dou L by dou theta, whatever we did, right? That slope you need to measure at each step. From the top, I took one step. Again, I have to see which way is the more steep. So that's the dou L by dou theta calculated again. Next, move further, calculate dou L by dou theta again, move further, and so on. So that is what is required. So that's why this equation is very important. It is called as a gradient descent. Okay, now coming to the data. So leave that example. It's done. We are fine with that. We understood what exactly is happening with that help, with the help of that example. Now let's move further. Now coming to the exact problem under the machine learning, there are different versions of gradient descent. So the first one is called as the stochastic gradient descent, in the sense, right, what I do, I update the theta value, I apply this equation and I update the theta value every time I pass a data. In the sense, first row is given, first row calculates a y cap minus y gives you a that is cost function, calculate a gradient out of it and update the theta value. Next, second row comes, second row is given, once again repeat this. So if you have 1000 data points in your matrix, this theta is calculated 1000 times. That kind of calculation is what is called as stochastic gradient descent. Why the word stochastic comes into picture? There is a facility that you don't have to give all the 1000 in the same order. Pick up randomly. First one, 10th one, 100, then coming back to 2, then going back to 999, and you can jump, right? So that is there. That's why it is a randomly picking up. So stochasticity is there. That's why it is a stochastic gradient descent. One at a time. Every data point goes, you update your this thing. Like every step you have to do that. There is another method. Okay. So now I'll try to bring another word. Okay. So let me use that word here itself. Okay, there is what is called as, I'll write, okay, if at all I have, if m data points, that means I have to do m iteration. The learning happens m times for one complete data set. Just understand that m iteration. Once the machine sees one data set completely, all the m values are given to the machine, means that is one epoch. Very important. We see these words many times, so I'm defining it right away. Right? At the beginning itself, we should understand what is iteration. Every times a loop runs is an iteration, but for a complete data set, iterations may be different. In this case, you see, one by one I am giving. When the machine is going to see all the data, then only it is called as one epoch. Okay, fine. So then the next version is called as the batch gradient descent, in the sense the complete data set is given at once. So at the end of 1000 data set, machine will update the theta value. Okay, so there is one iteration. In this case, complete data set goes into the machine, right, as a single data set. So at the end of that 1000, it will update, right? So one, in this case, you see one iteration means, that means the one epoch, correct, in this case, because that's the what is called as the batch gradient descent. Is it okay? Any doubt, please?
They don't have any equations.
No, equations are not required, right? I'm saying that how do you pass the data to the machine? Equations are not required, right? I don't want to bring unnecessary equations and make it complicated, first thing. And again, second case, in this case, no equations at all. I don't want to write my own, all right? Okay.
And sir, in
yeah.
this M is the number of rows we
Yeah.
are talking about.
M is the number of rows we are talking. Okay.
So after the after the last iteration, it will call a one epoch.
No. See the difference. That's my point. So iteration is different, epoch is different. Okay. Once computer is going to see all your data once, right? That means one epoch. But for seeing all the data depends upon how you feed the data. I give one by first row first, I update. Second row, I update. Third row, I update. That means it is the first method, that is called as stochastic gradient descent. Okay, step by step. Every data goes. Now you see there are m iterations because m times I am feeding the data. But once all the m is complete, you will see that, right, there is a ending of one epoch. But the second case is all the m data will go at once. Okay, only one iteration. That means in this case only one epoch. One epoch is one iteration in case of the batch gradient descent.
Batch.
So that is a fundamental difference. Yes. Others, if you have any
the basic difference. So the basic difference is in the first one, stochastic. That's what we call it. Stochastic gradient descent. The mth row goes one by one and update.
Yes.
Right. After completing, it will call a one epoch. But in the second one, it will go one by one and it will call one epoch.
It's not one by one. All of them will go together. All m will go together, right? So iterations, there are no step-by-step iterations. Everything will go at once. So machine is going to see all data at once. That's why only one iteration. That means one epoch. Okay. Epoch means the, so it's a time taken to see all data. That's all. Okay. That's what is the epoch. So
just a general term, right?
Epoch is that. Yes.
Okay.
All right. So now,
sir.
Yes. Go ahead, David.
Sir, this batch gradient discrete.
Descent.
So batch means like
complete batch. The whole data set is called as a batch.
Complete batch. Okay.
Yes.
Okay. Got it.
So that is batch. So batch goes at once. So everything you can see at once. That's why one iteration. All right.
Any limitation?
No such limitations. These are the options you have. That's all. You can choose. You can do trial and error and pick which is the best one for you. Okay.
Okay.
So fine. Fine. Okay. So now we understood that. So far, whatever we understood, I'll try to tell in brief. Right. So we had a question. We selected the various x parameters, right, and we had a y. So we had a normal equation to fit what is called as a linear regression. We can calculate the parameters theta, right? Using that, then the various options of selection of data and separation of the what you call as training data, testing data, etc. are done. And training options you have seen. How you feed the data into machine, what are the options you have, how to get an optimization value using a graph we have seen, etc. are there. Now, in case of a machine learning, there are something called as a hyperparameters. Okay, I'm going to write that now. So parameters are what you understood. there is again, with respect to each of the algorithm, you have what is called as a hyperparameter. That means those values which we can decide. For example, the one such this thing is called as it's an eta, right? This is the learning rate. As I told, we can initialize any value. We can put a value between 0 and 1, right? But you choose. You can choose. It's something like what you are comfortable with when you come down from a hill, right? If you keep a larger steps, you may fall. If you put a very small step, you may take a lot of time to reach bottom. So there has to be a balance, right? Using which you do. So this is one parameter which we call as the hyperparameter. Again, in some of the algorithms, again, this concept I'm talking in general with respect to the machine learning algorithms. Again, this is applicable for batch as well. You can decide what is called as another parameter, that is called as the number of iterations. We can decide. All right. So applicable to the batch GD as well, batch gradient descent as well. Right. So these kind of parameters will come. Other parameters, I will not put the names here because we are not aware of that. Because of other machine learning algorithms, they have different hyperparameters. I'm not going to put the name here because anyway, we have no idea what are they. So I don't want to waste time. Okay. So hyperparameters are something which I can do. The parameters are something which machine decides. Okay, so there is a clear-cut difference. Okay, so again, we are open for questions. If you have any question, please go ahead.
So, sir, this hyperparameter, it means suppose I will select batch size, right? And I will put like 4 times. So whole batch iteration will happen 4 times. Yeah,
it's going to happen like that, but you see, we will not go to the mini batch. Actually, you whatever you told, it actually is another type of gradient descent, but we are not using that under machine learning. We will use that under neural networks. Okay, so anyway, that's why I never touched that point right now. There is another concept called as mini batch. So there is what is called as giving one by one, stochastic, giving everything once, batch. Again, you can do what is called as I can decide. Something like I will not give the 1000 data at once. I'll give 250 at once. Okay, I'll split it into 4 pieces as you told. That comes under neural networks, not under machine learning. Okay, so yes, what you told is also a hyperparameter, but as of now, that's not going to be considered under ML. Okay.
So what is exactly mean by like number of iterations, sir, in hyperparameter?
So you can decide, right? How many times you want to, it says that, see, I am going to give the complete data at once, correct? I can say that how many times I want to repeat this process, right? I can ask the machine, repeat this 1000 times. Yes, I can do that. See, number of iterations is that, correct?
Okay. But what will be the benefit, sir? What will be the benefit of hyperparameter?
Hyperparameter is going to, it gives the user to decide something about the algorithm that he is going to build, right? So you see, in the sense, training a machine 50 times and training a machine 100 times has a difference. Like reading a paper, reading something, a document 50 times and reading the same document 100 times, there will be a difference. Like I may get more insight when I read more times. It's something like that. Okay. So training more times will definitely make the machine optimize the parameters better. Right. So you have a freedom to decide that how many times you want to train.
So number of iteration or learning rate, both are different, sir, right?
Yeah, both are different. Learning rate is different. Learning rate in the sense from the top to reach the bottom, what is the step size that you take? Little step you take, right? So if it is very small, you may take a lot of time to reach the bottom. If you jump and come, you may fall. Like algorithm may fail. It's like that. Okay, so that is learning rate. The eta value in the equation is the learning rate. But that whole equation, how many times you want to repeat, can be considered as the number of times you repeat the algorithm. That is what is the iteration. Okay?
Okay, got it.
Sure. Any other question? All right. Time for test. let's go ahead with these questions. Yeah, we have 2 minutes to answer. Let's try to recall what is a batch, right? Batch gradient descent in the sense all the data points will be fed into the machine in a single step. So the number of data points still remains same, but I am feeding them at once. So the question says if there are m, right, data points for training, how many of them will be seen by the machine, right? How many data points will be, right, will go into the batch GD? So the answer should be m, right? All of them will go at once. Okay, right? Just cross check your answers and right, try to understand. And if you have doubt, please ask. So the second part of the question, which of the following is true? Right? It says batch GD is a stochastic. Stochastic means what? One by one. And you have a freedom to choose at random. That's why the stochastic comes into picture. But when I feed the data at once, all goes in at once. There is no choosing options. Everything has to go at once. So this is not true. So second one, when SGD sees all the data points, correct? Every m point will go into the machine. That means it is called as one epoch, right? That is correct. Mini batch GD is a deterministic algorithm. Anyway, we have not worried about that. So that's wrong. So just to fill it, we have written that batch GD uses one data at a time. That's also wrong. All right. So you can see that, right? The one point which we have understood so far is when SGD sees all points at once, it is called as an epoch. So the next point, which of the following are the hyperparameters of batch GD? So batch GD, in the sense everything will go at once. You have a complete freedom to choose learning rate. What is the eta value you can choose? What are the number of iterations you want to, how many times you want to repeat that also you can choose. Okay, so size of batch, no option. All the m should go at once. Sampling, there is no question of sampling as of now, so just rule it out. So, okay, so as you can see, these are the correct answers. Okay, I can see a few of you have given that answer.
Excuse me, sir. Sir, in question number third, sir, we are talking about the batch GD, and in batch GD we have only one iteration. Then how we can choose the number of iterations? Number of iteration in the sense I can feed all data at once. That is called as one iteration. But I can say how many times I can repeat that, right? The whole batch goes into the machine. How many times I can repeat, right? Okay. So fine. One iteration means what? In batch GD, one iteration and one epoch are same. Okay, that was the point which I mentioned in the previous page. But now the point is that how many times I want to train the machine with the same data, I can decide, right? I can keep feeding the data 1000 times, right? So that is what is the number of iteration.
Excuse me, sir. Could you explain learning rate in this case?
Yeah, learning rate in the sense, just you need to analyze, right? There was an equation, right? So just let's go back to the eta which you see here is the learning this thing. So in the sense, irrespective of which gradient descent you use, you are going to use the same equation. Theta k plus 1 is theta k minus eta times the gradient of that function. So this eta is what is called as a learning rate. In order to optimize the theta from a starting point to the theta star, right? I can say that this is my step size. I can go this step. So from the top, you want to come down, you will go with the step-by-step procedure. What is that size of the step that you want to stay, right? Is called as a learning rate. All right. So if you keep it very small, it is going to take a lot of time to reach the bottom from the top. But if you keep a larger size, right, you may fall down, right? When you're coming down from a hill, you try to keep a very large step size. Definitely you lose balance and fail. Same thing is going to happen with the machine learning. So algorithm may fail, okay, may not be able to reach the optimum form. That's the problem. Okay, so that's what is the significance of the learning rate in this case.
In case of hyperparameter, sir, hyperparameter, how it is connected with hyperparameter, right?
That itself is called as hyperparameter. I can decide that, right? So whatever in the algorithm, what you can decide, what are the parameters you can decide is a hyperparameter. Okay. So I can decide this, so I am calling that as a hyperparameter. Okay.
Fine.
Sure. All right. So we are coming to the last part, right? This is how can you make sure that machine has learned properly, right? So this is called as the goodness of the fit. So whatever curve fitting you have done, right? Whatever is the straight line that you have designed because of the parameters, machine has learned something. How good is that? Is it really good or is it bad? Something like that we can measure. For that, we use a parameter that is called as a R square parameter. It is a R square. The notation is R square. Y square, there is no answer. Somebody has denoted that by R square, so everybody is using that. So it is called as the coefficient of determination, or it's also called as the coefficient of the regression, right? So what is the equation, right? The equation is very simple. The R square can be calculated as 1 minus sum of all the values, summation over j. J is the row. I have to calculate the yj minus y cap of j, the whole square, whole divided by, only division is happening to only this term, not the 1. 1 is outside. 1 minus this whole term. So I'll put a bracket here. Okay. So divided by, again, summation of all the rows. This is yj minus the y bar the whole square. What is y cap? We know it's an estimation. The y bar is the mean value, mean of y. The whole y column, you have some mean, right? You have to calculate the mean. So using that, you can calculate this, right? This y. So this r square. So use this equation and you calculate r. Now, how do you find out whether it is a good fit or not? This is the solution. Okay. Say, right? So this is the case. R square is close to 1 means that is a good fit. Okay. So if R square is closer to 0, that is a mean fit. In a sense, okay. Okay. So you have to make sure that the predictions are coming closer to y, means R square value when you calculate, that should be coming closer to 1. Like a percentage, right? So closer to 1, if you get 0.89, you can say that 89% of your fit is good. At the same time, if the R square value comes to very close to say 0.15, you can say that only 15% of your values are actually predicted correctly, others are wrong. Okay, so this is the whole concept called as linear regression. All right, so upcoming session, we will be directly jumping into the coding part of what we had defined as a problem at the beginning of today's session. All right, any doubts?
So one.
Yes, Gaurav.
And what if, is there any value for the bad fit?
No, we said bad as the mean fit only. It's okay, right? Bad means if you come exactly 0, that makes no sense. There is no fitting.
It's a bad fit.
Okay, that's
okay.
Right. Any value comes closer to 0, it's a bad one. All right.
Sure.
Okay. Any other note?
Hello, sir.
Yes, Devendra. Please go ahead.
So I think we was trying to find out a theta value at minimum, right, sir? So we can stop. We can end our program.
Not theta minimum. Loss is minimum. Theta is not minimum. Loss is minimum. Yes.
Yeah.
Okay.
And after the loss, like we have to validate also by the R square.
Yes. R square is a measure. Just to say that whether whatever you have done is good or not, you can identify using.
Yeah.
Okay. Because calculation of loss is difficult for whenever data set is too huge. Every time you calculate loss and do something is difficult. For that reason, we are trying, you see, actually this is a loss only, right? If you see the numerator term, what is that? There is a loss present in this term, correct? We are using the loss in some sense to calculate a R square. Somehow they are related only. Okay.
Okay.
Sure.